morning, everybody. Here's part 2 of our equilibrium, and today we're going to start putting some values in here to figure out the equilibrium constant. And how we're going to do that is we are going to use the law of mass action, and it gives a general description of this equilibrium condition. This works very well, except in conditions of very, very high pressure and very saturated solutions. So it would be in situations where things couldn't act randomly, then maybe this law wouldn't work. So most of the time in what we're doing in here, it is going to work. So again, it's a balanced equation. You can see J, K, L, and M are just our coefficients. So our equilibrium expression, this is a very important point, is that the reactants and the products must be gaseous or in a solution to be included. I think I just mentioned that they have to be able to act randomly. Well, solids and liquids at the surface, they can't act randomly, so we are not going to put them in our equilibrium expression. So, and they are temperature dependent. So some ways that you might see the equilibrium constant written, because again, we're writing using various books and things in AP World. So it could be EQ for equilibrium constant, that sort of makes sense. It might be, say, Kc for the concentration of the equilibrium expression, or they might just simply write K. So just be prepared for any of those. So our law of mass action says, whichever way you're going to write your equilibrium constant, so K is equal to the concentration of our products, so C, if I use my equation from above, raised to the L power, concentration of D, raised to the coefficient, the M power, all over my reactants. Concentration of A raised to the J power, concentration of B raised to the K power. And so you're going to hear me say a lot that it is actually the concentration of our products raised to the coefficients over our concentration of our reactants raised to their coefficients. And so this is going to be our law of mass action. Now this is in terms of concentration. The other thing you need to know is that we can write the same thing if we are talking about something that is pressure related. So if we're talking about gas laws and we're talking about Pivnert, we can still find the equilibrium expression for that too. And most of the time you will see that. I have never seen it any other way than that. So that would be the pressure, our equilibrium constant when we're in terms of pressure. And instead of, remember, brackets mean concentration, we can't use brackets. So it is going to be our partial pressure of C raised to the L power, if I use the same equation up above, the pressure of D raised to the M power, all over, it's still products over reactants, the pressure of A raised to its power, and then the pressure of B raised to its power. So again, it's still the pressure of the products over the pressure of the reactants. So it's still pressure or products over reactants in whichever way you're taking a look at it. Okay, so let's put some numbers in here. I think looking at that might be a little overwhelming, but actually when we start putting numbers in here, this isn't bad at all. You can go ahead and read that note that K is constant no matter what the initial concentrations. The important part is that each set of equilibrium concentration is an equilibrium position, okay? There are infinite number of positions, but only one constant. So I can do experiment, what that means, I can do experiment 1, 2, 3, 4, all the way out to infinity, but there's only going to be one equilibrium constant. The particular set of conditions, remember, just think about our classroom. That is a set of conditions. So here's our first example. It says, given a concentration of nitrogen gas at that molarity reacting with hydrogen gas to produce ammonia gas at equilibrium, calculate the equilibrium constant. As before, when it sounds like I can write an equation, I should write an equation. It says reacting with. I know that nitrogen is diatomic, so that's going to be N2. And I know that hydrogen is also diatomic, so that's going to be H2. And it says at equilibrium, so I have my forward and backward arrows. ammonia is NH3, and it also tells us that that is a gas. Now, the reason that that is important, that means I can put everything in my equilibrium expression, because remember, they have to be gases or they have to be aqueous. They have to be able to act randomly. Can't forget to balance. Okay, so if I go up and I write down, it says the concentration of each one of these now, and I am given concentration in molarity, so I'm going to use my brackets. 0.85 is the molarity of my nitrogen. My hydrogen is 0.0031. Oh, sorry about those zeros there. And my ammonia is 0.031. So those are my concentrations. So now I'm just going to put it in my equilibrium expression using the law of mass action formula that I just gave you. So it is, remember, product over reactant. So I'm going to say that my equilibrium expression, which I want you to write your expressions first, is my product. So it's my concentration of NH3 raised to the coefficient of 2 over my reactants. So products over reactants, concentration of N2 raised to the coefficient, which is 1, and then concentration of my hydrogen gas raised to its coefficient, which is 3. Now in this situation, these are going to be easy ones to take a look at because everything is given. Once we start having to manipulate what the equilibrium expression would be for either nitrogen or hydrogen, or even ammonia, that's when it's going to get a little harder. So I can just substitute my numbers in. So my concentration of my ammonia is 0.031 raised to the second power. I have a concentration of 0.85 for my nitrogen gas, 0.0031 for my hydrogen raised to the third power. Punch that all in my calculator, and I get 3.8 times 10 to the 4th. Now, because we are always doing products over reactants, and that means the units are always going to cancel out. So we do not have to worry about units for K. It is always just a number, okay? All right, now, we just said that things can go in the reverse reaction. So we wrote this all in the forward direction. What about if it's in the reverse? Well, if I'm going to consider the reverse, I think you could recognize that I can just write that I have 2NH3 reaching equilibrium. When it decomposes, I get nitrogen gas plus 3 parts of hydrogen gas. Well, it's just going to be flipped in the exact opposite direction. So if it is flipped and the forward direction is K, I hope it would make sense to you that when I go in the reverse direction, that it is equal to 1 over K. So what that means is I can just take my equilibrium constant from the forward reaction, flip it to put it into the reverse, because that's all I'm doing is reversing the reaction. And so when I calculate that out, I get 2.6 times 10 to the negative 5th. Now, could I have put in all of those values and done it and flipped it? Absolutely. But we just want you to be able to see how you can manipulate an equation, and that if you double it, you square it, or whatever you're doing to the equation, you can do the same thing to K. All right, so this should give you enough to get through some book questions on equilibrium concentration, and then we can continue to talk about how to solve it when we don't have all of these components. You guys have a wonderful day.